started. Alrighty, welcome everybody. This is going to be AP Physics Review, Unit 3, Multiple Choice Questions A. So here's our first question. Planet X has a mass of big M and a radius r. Planet Y has a mass of 3m and a radius of 3r. Identical satellites orbit both planets at a distance r above their surfaces. The planets are separated by such a large distance that the gravitational forces between them is negligible. So here they've drawn these two planets next to each other, but they're not necessarily next to each other. And the question is, how does the force, or how does the magnitude of the gravitational force Y exerted by planet Y on its satellite compare to the gravitational force Fx exerted by planet X on its satellite? So each of these planets are going to be pulling on a satellite, and they want us to compare the forces. Let's go ahead and see what we are thinking. And so we may need a reminder on or refresher on equations. Yeah, so in this unit, one of the big ones is the gravitational force is given by Newton's law of universal gravitation. And on your AP equation sheet, it will be showing up something like this. And we'll go ahead and call it at 45. If you don't have time to answer it, that is totally fine. Just kind of give you a chance to answer here if you can. Okay, so let's go ahead and take a look at what this tells us. So the force due to gravity is going to depend on some universal constant. That's big G here. Now, very important. This is not the acceleration due to gravity. It's some constant that tells us how powerful gravitation actually is. And it's absolutely pathetically weak, but it's a number nonetheless. M1 is going to be one of the two masses involved. So this could be M1 or this could be M1. It doesn't really matter who M1 is, but it's going to be one of the masses in your system that you are considering for the gravitational force. I usually let M1 be the big mass and M2 is going to be the smaller mass, which in this case, I'm going to go ahead and say that this is M1 and this is M2. And we're going to do two calculations. We're going to do the calculation for this system and the force for this system. And we're going to go ahead and make a comparison there. Okay, so if we look at this scenario, we ask ourselves, well, what's the mass of this guy? Well, that's big M. And then what's the mass of the satellite? Well, it's the mass of the satellite. And then we ask ourselves, well, what is R? R is going to be the distance between them squared. And so here it's going to be from here to here. That's a quantity of 2R. And then we're going to have to square that bad boy. So this will be the force due to gravity between the objects in planet or system X. Okay. Let me know if you have any questions so far. I do not have the chat open. Sorry for that. That way I can see here if we do have questions. So to kind of answer this question quickly, you're best off looking at what is changing in each of these scenarios and dealing with proportionalities. All right, no problem. Okay. So in this case, really the only thing that's changing is the big mass, which I'm going to call M1, and the distance between the other two. So when we deal with comparisons like this, we usually call them proportionalities, and we don't worry about the other things. The satellites are going to be identical in both cases. Yeah, the extra R plays a gank in this one. So if we look at this, it's going to be big M over 2R quantity squared for the force due to gravity on system X or in system X. So that's going to be something like 4R squared. Okay. Now let's go ahead and do this for the force due to gravity on system Y. Well, again, we're not going to worry about G. We're not going to worry about the mass of the satellite. All that really matters is the mass of the planet and the radius here. So in this instance, mass 1, well, that's just the mass of the planet, 3m. And then we ask ourselves, well, what's the orbiting distance? Well, by golly, it's 3 times the radius, but we're still a distance r away. So the distance between these two objects is going to be 4r. And then we're going to square that monster. And so this becomes the force due to gravity on y is going to be 3m over 16 r squared. And so when we make a comparison, it's m over 4r squared versus 3m over 16. If we divide these two, we find out that we get a ratio of 3 over 4. The m's cancel out, the r's cancel out. We have 3/16 versus 1/4. You can kind of think of this as 3 over 4 times 4 versus 1 over 4. And so one of these 4's cancels out into comparisons. And so the force due to gravity on planet Y is going to be 3/4 the planet, the force due to gravity on X. So let me know if we have questions over that, because this one can seem really tricky. Oh, nice. You got it? Excellent. Let's go ahead and look at question 2. How does the gravitational field G of X at the surface of the planet? So this one is asking, how does the gravitational field, so that's G of X at the surface of planet X compare to the gravitational field at the surface of Y? So we'll go ahead and do a poll here. And so relaunch polling. Let's go ahead and take a look here. Okay, and I'll hold a couple more seconds. I'm just going to write here something for the future, but hopefully you guys recognize it. So R in this question is from the center to the surface, which is a little different than the first question. In this case, because they wanted the gravitational force to the satellite, R is the distance from the center to where the satellite is. Because we want to get the gravitational force on the satellite, we needed to have used 4r in the previous example in y. But here, because we're just talking about the surface, that'll change our r. Okay, so we're going to go ahead and end the polling here. Hopefully we were able to get some answers. So if we look at this, the gravitational force divided by the mass of the satellite is going to give us G. And so again, if we look at what's changing, well, the mass of the satellite doesn't really matter here. It's just G times the mass of the planet over r squared. And G is a constant. We don't really need to worry about that. What's really just going to change is the mass of the planet and the radius to the surface. So the radius to the surface of X is just r, and the radius to the surface of planet Y here is where you can go ahead and use 3r. Okay, so what ends up happening is G of X is going to be big M over r squared. Nothing fancy here, actually big R, because he tells that it's big R. G of Y, or the gravitational field strength on planet Y, is going to be 3m over 3r quantity squared, which becomes 3m over 9r squared. So then we just compare these two quantities. Well, if we clean this up, what we get is, well, 3/9, that's 1/3 m divided by r squared. And G of X is already mr squared. So hopefully we can recognize that g on planet X is basically this part right here. And really, g of y is then going to be the acceleration due to gravity on planet Y at the surface is going to be 1/3 the acceleration due to gravity on planet X. So I think here, if we notice, none of our answers are showing up in this way. But we can go ahead and say g of x is really 3 times g of y. And so B is our best answer here. You had used 4m instead of 3m. Oh, that's a shame. I'm sorry to hear that. Yeah, these numbers can get really confusing to keep track of. So
there's a lot of stuff here that's going on.
Howdy, Richard. Let me know if you have questions. And then you forgot to use the 3m. Yeah, there's a lot of stuff going on here. There's 2 sets of numbers that we're doing our calculations with, and we're doing 2 different calculations with it. Good thing we have plenty of practice here. So we have a planet and a moon, and they tell us a moon orbits a planet in a circular orbit of radius r as shown in the figure. And they ask us, which of the following free body diagrams could be used to analyze the forces exerted on the moon when it is at the position indicated in the figure? So here I'm going to have to zoom out, and I do apologize if that makes it a little harder to see. But our moon is going to be to the left of the planet, and these are the 4 free body diagrams. So why isn't it 1/3? Oh, sorry. So while you guys are working on this one, let me pause the share real quick. And then, or actually I need to resume it. So if we look at our statement here that we wrote for the previous question, we see that g of y is 1/3 g of x. And this guy has it backwards. They're telling us that g on x is going to be 1/3 g on y. Does that make sense there? And if not, let me know. Yeah, so that's the big gotcha, because if you see 1/3, you're going to be like, well, the previous question had the fraction written correctly. So then, like, we need to be a little more astute there and keep an eye out for that little switcheroo, which is why we have to kind of like switch it around and say, yeah, no, definitely. The College Board.
I have a question.
Go ahead.
So in this orbit system, the Earth exerts a gravitational field on the moon, but does the moon exert any sort of gravitational field on the Earth?
Yes. So really important. When this is why I keep saying, like, when the Earth pulls on you, you pull on the Earth. Together, you guys exert this amount of force between each other. So when the Earth pulls on you, let's say you weigh 100 pounds or 100 newtons. The Earth is pulling on you with a force of 100 newtons or 100 pounds. And you are also exerting that equal and opposite force on the Earth. So you're pulling the Earth up towards you. It's just the Earth is like way more massive than you. And so its acceleration when you fall towards the Earth is dang near negligible. It will be 10 to the 24th times less as the acceleration. It'll move less than an atom. As a matter of fact, the distance that it moves is on the same scale or size as an atom is to us, as that distance is to the size of an atom. So it's absolutely tiny. So yes, very important. You exert equal and opposite forces. So here, when we draw our free body diagram, really important. There's no such thing as a centripetal force acting on this as an external force. The most popular answer choice here was C. We had a couple of people say D. These are not actual forces. We have the force due to gravity pulling us towards the center, and that's the only force that is acting on this moon. And in this case, because this is the only force moving the moon in a circular fashion, this is the centripetal force. So we could say, since the force due to gravity is the only force. Okay, yes, I'll explain what centripetal force is and then centrifugal. So since the force due to gravity is the only force causing this circular motion, it is the centripetal force. So let's go ahead and redefine the centripetal force real quick. So centripetal force is the name we call the net force that points towards the center of a circular path. So it's just a title. It is not its own separate force. One way you can think about it is if you look at all those kings of Europe, or even queens, they are given a certain birth name. And I don't remember any of these kings and their birth names, or queens and their birth names. But when, or even the Pope, this happens with the Pope. You're born with a certain name. And if you ascend to the status of king or the status of Pope, you choose your kingly name. And that's what goes down in history. So like, for instance, let's just say, I don't know, King Henry VIII was really born as like Richard Tudor or whatever the hell his family is. When he became king, he decided to be Henry VIII or whatever. And I'm just making that up. I don't know if that's like the exact, maybe he was actually born Henry. But
Well, actually, sir, I think you're kind of right. But like, I think the thing is like they when the parents are naming them, like they make their middle name. I think this only happens in, they make their, so like the Queen of England, what his name is like Alexandria Elizabeth May or something like that.
Okay, I see. So yeah, like for instance, and I see this more like just because I grew up in a Catholic household. Popes would have a different name. Like for instance, the previous Pope, I don't know. He had a certain name, and then when he became Pope, he got that new title. So whenever you're talking about the centripetal force, it's a similar idea. These forces have their original names. And when those forces become the net force acting towards the center of the path, then we redub it the centripetal force. So like, here's an example. If we remember when we were doing our roller coasters, let's say I have a roller coaster at the top here. If I draw the free body diagram of my cart, there's the gravitational force from the cart, or on the cart, sorry, by the earth. And then if we notice, it's on a surface pushing it, and the normal force here would be pushing down. So in this case, the net force would be the normal force plus the force due to gravity, because they work together. And the other part, this is something going back to circular motion. When an object moves in a circular path, we say towards the center is the positive direction.
What about that like fake force that you said that was like if something's in a circular motion, like its inertia will try and force it to move to a line tangential out of its orbit.
So we'll get to that one right now in a second, because yes, that's the next point here. So here, these two forces are positive and they point towards the center. So that's why they're positive. And in this case, all of this right here is the centripetal force in this scenario. Okay, let me give you guys another example. Let's say the cart now is at the bottom, and then I'll get to your question, Noe, sorry. Oh, I should try to like keep things anonymous just in case, because I'm posting these on the internet. So let's say my cart here is on the bottom of the loop. If I draw my free body diagram, here, the normal force is pointing to the top because the surface is holding us up, and the force due to gravity is pointing down. In this scenario, the net force would be, well, up in this location here. So that's the crazy thing about circular problems. The positive direction is continuously changing as you go around the loop. It always is considered to the center, but to the center is going to have slightly different directions depending on where you are. And so in this case, the net force would be the normal force minus the force due to gravity. And we would say here, this is the centripetal force. So the centripetal force is going to change in every scenario. And then just real quick, let's say it's off to the side. When it's off to the side, the normal force acts this way, and the force due to gravity is acting this way. So let's look at what the centripetal force looks like in this scenario. Well, in this scenario, we only have one force pointing towards the center. And so the net force towards the center, oh no, my tablet is flipping out, okay, would be the normal force. Now here, because the force due to gravity does not act in the same direction, we do not consider it. Remember that for forces, we want to break it up into two directions that are perpendicular. That's not a good color. So in this scenario, we would have kind of like y, and we could choose positive y to be up, or we could say negative y to be up. And then we would have this x direction be our other direction. Okay, so really important here, the equation for the net force towards the center is just n. And this guy here is the only thing being the centripetal force when it's off to the side. We would also need to, or we could also do a net force in the vertical direction in this case. And in this case, it would be like the force due to gravity equals m times a, but this acceleration would be the vertical acceleration. Okay, so it gets really tricky when we're off to the side, because when we're off to the side, when we're considering the centripetal force, we only look at the thing that's pointing towards the center. And we say that's the centripetal direction. So what is the centrifugal force then? Well, the centrifugal force is not really a force. It is this effect that you feel. We call them fictitious forces. I don't know if you guys got a chance to watch that frames of reference video I posted. But let's say I am in in this accelerating frame. When I'm at the top, at this very instant, when I am here at the peak, my body has a mass and it has velocity in this direction. And I'm going to want to keep that mass and that velocity until a net force acts on me. So what ends up happening is at every instant, your body wants to shoot off in a line tangent to the path. But the surface is providing that inward force. And so you feel a force in the opposite direction of your acceleration. And when you feel that outward force in a circular path, you're going to, we call that the centrifugal force, but you never, never, never add it on the free body diagram. That is asking for death from the College Board, okay? So we say in physics, this is a fictitious force. It is not really there. Fictitious, hopefully I spelled that right, force. And what does fictitious mean in physics? Well, it means it doesn't exist, but we feel like it's there. So for instance, if I'm in a car and I accelerate forward, my body feels a force pushing me back. So there's this fictitious force in your mind. Your body says, well, my body feels it's being pushed back. There's got to be a force back, but it's not really what's going on. It's that the seat is pushing back into you and you feel like you're being pushed more into your seat, when in reality, the seat is squeezing forward into you, accelerating you. If you hit the brakes and the seatbelt is on you, yes. So really important. The centripetal force is another name for the sum of forces that cause circular or to an extent elliptical motion. Yes. If I hit the brakes decelerating, I feel like I'm being pushed forward, but what's really going on, and that forward force would be considered a fictitious force. It's not really there. What's really happening is your seat is pushing back on you, trying to slow you down, or your seatbelt's on. So when you move around oh, go ahead.
So that force isn't due to, there's no increment in the acceleration due to gravity. It's just your inertia making you feel like the acceleration due to gravity is higher.
Exactly. You feel heavier when you're turning here. So like When you're being accelerated inward, you feel like you're being pushed outward, but that's because the surface is continuously pushing you in. So you press more and more into that surface because your body wants to leave that path. All objects want to move in straight lines at constant speed. So like, for instance, if this planet was not here at this instant, let's just say for whatever reason, I obliterate it such that it does not, like the obliteration does not affect the moon. At that instant, the moon would just continue in this velocity. There is a game called Space Engine or Universe Sandbox. I don't, don't buy it. Don't go spend money on it if you don't have the money or don't want to. But you can actually practice this. You get rid of the planet and it does all the calculations of physics simulations to figure out what's going to happen to the motion of the moon or a planet, and it's just going to shoot straight forward. If I happened to fire or to destroy the planet when it's right here, then the moon would shoot off straight or it would shoot off in a straight line like this. Other questions? Yeah, this is a heavy topic, but hopefully that makes sense. So in this case, really our two answer choices are either A or B, and hopefully we recognize that the moon is going to be forced towards the planet to move around in a circular path. Let's go ahead and take a look at the next question here. I'm going to zoom in a fair bit. So it tells us the moon has a mass of 10 to the 22 kilograms, and the gravitational field strength at a distance r from the planet is 0.001 newtons per kilogram. That's this scenario. So they give us the mass of this moon, and when it is at this distance from the planet, it feels this much gravitational field strength. And they want us to find out what is the gravitational force exerted on the moon while it is in orbit with the planet or around the planet. Okay, we'll go ahead and call it here. Hopefully you guys got a chance to submit an answer. If not, no worries. So we have learned that the force due to gravity is mass times g. And we usually call this the acceleration due to gravity. But that's just what we find out experimentally. Really, this is the gravitational field strength, which just happens to have units of acceleration. So let's go ahead and take our numbers. We have 1 times 10 to the 22 kilograms. And hopefully here they recognize that if all else fails, you can look at the units and recognize that if you multiply them, this is going to be, oops, I put the units in the wrong spot. Newtons per kilogram. And so you could go ahead and type this out into your calculator. I guess one way I would look at this is I would need to remove 1, 2, 3 zeros from this number. So hopefully we find out that this comes out to 1 times 10 to the positive 19 newtons B. There's another way you could do it scientifically. This becomes 1 times 10 to the 22 kilograms times 1 times 10 to the negative 3 kilograms. And when you multiply the first parts, which comes out to 1, and then you add the exponents of this part. And so that becomes times 10 to the 19 newtons. Another way you could have gotten this answer is recognizing, okay, if I multiply these, this number is going to make this number smaller. So D should hopefully be out. No one chose A, thankfully. A lot of people would probably think A because we're told or led to believe there's no gravity in space. If there was no gravity in space, this bad boy would shoot off to in a straight line. But really important, the gravitational influence of any mass extends infinitely far away in the universe. It's just that the force gets so weak with distance that usually we don't get to pull, another galaxy towards us, or we get pulled. All right, you have to go somewhere, no worries. Have a good one. And then I will definitely try to get these videos uploaded tonight so that you guys can watch them on your own time. Astronomers.
Question.
Uh-huh.
So you said that the force of gravity extends infinitely, just that it gets like exponentially diminished and whatnot. Can we use or can we detect any of these like resultant forces and use them in any kind of detector to detect celestial bodies anymore?
So we kind of do that with telescopes. We look at the wobble of a planet to try to figure out how much mass is orbiting it. And then from there, we can figure out, okay, if we are able to zoom in, I guess, enough, we can see how far or how big that orbit is. And then measuring the time of the wobble, that will tell us essentially how much mass is orbiting something. But really important, do not say exponentially. The force due to gravity is an inverse square law. So you would say it decreases to the power of -2, or it increases or decreases by the square of the distance, not exponentially. There is an exponent there, but when we say exponentially, we mean that the equation says e to the x or e to the -x. So be careful. The College Board actually gets really upset, or not upset, but they really think that this is bad. Unless you actually see e to the x in an equation, don't say exponentially. Just say to the power of. But yes, we can definitely do this. And so there's these things called gravitational wave interferometers, and they basically measure vibrations in space. As a matter of fact, for instance, let's see here. So Uranus was the first planet that was discovered with a telescope, if I'm not mistaken. When they did the calculations for the orbit of Uranus, they noticed that the calculations were slightly off compared to the experimental, or what they measured, values. So some scientists started theorizing and calculating and predicting, okay, if the orbit is this far off from the predicted or calculated values, then we think that there is a mass this far away orbiting the sun, causing this disturbance. And so that actually gave us Neptune. If I'm not mistaken, Neptune was discovered by scientists calculating its presence due to its disturbance on Uranus. All right. So let's go ahead and take a look at another one, unless you guys have questions. So it reads, astronomers making careful observations of the moon's orbit discover that the orbit is not perfectly circular, nor is it elliptical. Which of the following statements supports this observation? And so I believe this is a separate question, or it may actually be tied to these. But yeah, it's in reference to this. So what they find out is that the orbit is not perfectly circular, nor is it elliptical. And they say there's a couple of reasons here. Let's see which one is correct. We'll relaunch the polling. Okay, so that is 10. And so it turns out this is exactly what I was talking about right now. There's another body exerting the gravitational force on the moon. Really important. As far as we know, this will be the case everywhere in the universe. That's why it's called the gravitational constant. As far as we see, it's always the same. Whether you do relativity or Newton's laws of gravitation, this value is the same. The moon and the planet exert forces equal and opposite of equal magnitude on each other. This is always a given. This is, whether its orbit is circular or elliptical, this is always true. Newton's third law. These guys are an action-reaction pair. Okay. There is a centripetal force that causes the net force exerted on the moon to be different from from the gravitational force. Again, very important. We need to recognize that the gravitational force is providing the centripetal force. This is not a separate force. And so that leaves us with B as our best answer. Okay, let me know if we have questions over this one. But yeah, this is exactly what they found out for Uranus's orbit. And that's what led them to calculate the distance and the mass of Neptune. Okay. So let's go ahead and take a look at the next question. So we have two figures, each with two containers, and they say, two containers of water can have their masses varied by adding or removing water. The containers are initially a distance d apart as measured from their centers. Okay, 1 second, I'm trying to pull up the scroll. Oh man, things are going kaput today. There we go. As measured from their centers, and are filled with water so that each has a mass of big M as shown in figure 1. The gravitational force that one container exerts on the other is F naught, or F original. They tell us that water is added to one container so that its mass increases to 1.5 m, and water is removed from the other container so that its mass decreases to 0.5 m. So half of the mass was transferred from one container to the other. What is the new gravitational force exerted on the container by the other? So here's a mouthful. But basically, what's the difference, if any, in the gravitational force now that we have changed the mass and transferred it from one container to the other? All righty. We'll go ahead and call it at 30. And so let's go ahead and take a look here. So the most popular answer choice here was A. We had a couple of people thinking that the force would be the same because we're dealing with the same amount of mass, right? But the masses of the objects themselves have changed. Before we had big M times big M all over d squared. So we could say the force due to gravity at the beginning, or F original, was m squared over d squared. In this new scenario, we have 1.5 m times 0.5 m all over d squared. And so what's really changed is the mass here. And so what we get out of this is half of 1.5 is 0.75 m squared over d squared. And this quantity here was FO. So we get 0.75 FO in our answer, which is going to be 3/4. Answer choice A is the best one. Let me know if that made, if you guys have questions or if that made sense. But I think most of you guys were able to get that one. All right, let's go ahead and take a look at 7. Looks to me like we have two objects orbiting a planet, and it says satellite A orbits a planet at a distance d from the planet's center with a centripetal acceleration A original. A second satellite B orbits the same planet at a distance 2d from the planet's center with an acceleration, centripetal acceleration, sorry, AB. What is the centripetal acceleration AB in terms of AO? All righty, so let's go ahead and take a look at this one. So maybe we're thinking, hey, I learned that the centripetal acceleration is equivalent to v squared over r. The problem is we don't know their velocities here. So sadly, this won't help us out. We do know their distances, but we don't know if the velocity of this guy is exactly equal to this guy. Plot twist, it isn't. So here we need to think, well, what else is going to give us this centripetal acceleration? Well, the centripetal acceleration is also the centripetal force divided by the mass, or the net force pointing towards the center divided by the mass that is accelerating. So it's going to be the gravitational force pulls each of these guys towards the center of the planet. Gravity acts towards the center. So this guy has some gravitational force B acting on it. This other guy has a gravitational force called FG. I'll call FGA acting towards the center as well. And this guy has a mass B, and this guy has a mass A. We don't know them, but it turns out it doesn't matter, because for this, we get big G, mass of the planet, times mass of the satellite over r squared divided by the mass of the satellite. Doesn't really matter what mass A and B are, because to get the acceleration, we're going to need to take the gravitational force and divide it by the mass of that satellite. So mathematically, it's going to cancel out. And what we find out is that the acceleration, which is the gravitational force divided by the mass of the satellite, is given by big G, the mass of the planet, all over r squared. And again, big G is a constant in our comparison, so we don't need to worry about it. And the mass of the planet is also a constant in our comparison. What we find out is that the accelerations of these planets is given, or is proportional to 1 over r squared. The acceleration of A is 1 over d squared. The acceleration of B will be 1 over 2d quantity squared. So that becomes 1/4 d squared. So it's going to be 1/4 the centripetal acceleration of the first guy. So A is our best answer choice. Any questions over this? It's the gravitational acceleration, which is given by, so really important. We've seen that if I say mg equals, that's the force due to gravity, equals big G, m1, m2, all over r squared. Really, this is m2. This cancels out. And we have a formula for the gravitational field strength, or the acceleration due to gravity, G m1 over, or mass of the planet, over r squared. Okay, let's go ahead and look at this next one. Question 8. 2 students must conduct experiments so that the inertial mass and the gravitational mass of the same object can be determined. In the experiment, to find the object's gravitational mass, let me actually pull up the highlighter. Ooh, that is a tad too thick. The student ties one end of the string around the object with the other end tied to a spring scale so that the object can hang vertically at rest. In the experiment to find the object's inertial mass, the student uses a spring scale to pull the object from rest across a horizontal surface with a constant applied force, such that the frictional forces are considered to be negligible. In addition to the spring scale, the student has access to other measuring devices commonly found in science laboratories. Which of the following lists the essential measuring devices that the student can use to collect the data necessary to find the object's gravitational and inertial masses? righty, we'll go ahead and call it here. So in case we're wondering, well, what's inertial mass? What's gravitational mass? So inertial mass is the mass that we refer to when we say m times a, or net force. It is the mass experiencing a net force. Gravitational mass is the mass that we use when we think of mg, or big G, mass of 1, mass of 2, all over r squared. So these guys are considered gravitational masses. Now, what we find out experimentally is that these two are equivalent to what we call the inertial mass. The inertial mass is the mass that resists accelerations and forces. Gravitational mass is the mass that gives us weight. And just so happens that they are the same. So what do we need to measure this? Well, basically, we just need to get accelerations. If we can measure the acceleration due to gravity as it falls, or the acceleration of this block as we pull it, then we're done. A motion detector is redundant. The mass balance is also redundant. We already have a spring scale. A spring scale is basically a mass balance. They're the same thing. They measure how much force is acting on them when you're pulling or when you place the object on the scale. And lastly, this guy, yeah, this one's kind of like hopefully the obviously bad answer. So it turns out that essentially we just need a meter stick and a timer. We measure the displacement, we get the timer, and we're able to get accelerations from there. Let's go to question number 9. 2 experiments are conducted to determine the mass of an object. In experiment 1, object's weight is measured using an electronic balance once the object has been placed at rest on the balance. In experiment 2, the object is pulled along a horizontal surface with a spring scale such that the reading in the spring scale remains constant, while a motion detector is used to measure the instantaneous speed of the object as it is pulled. That is a very lengthy spring scale, force reading, motion detector is used. All frictional forces in both experiments are considered to be negligible. Which of the 2 experiments, if either, could be used to determine the gravitational mass of the object? Let's go ahead and see here. All righty, we'll go ahead and call it here. So this question is basically asking, which of these will let you get weight? Or which method uses weight? Remember, gravitational mass is the mass that gives you weight. So if we look at scenario 2, in experiment 2, they're pulling this guy with a force, and they're using a motion detector to get the instantaneous speed. If we can get the instantaneous speed as it changes with time, we can get the acceleration. So really important. Experiment 2 gives us the inertial mass. It is the mass dealing with a force acting on it as it accelerates. It is the mass that accelerates. In experiment 1, we're dealing with the mass that experiences weight. And again, let me know if we have questions. Number 10, a student analyzes data of the motion of a planet as it orbits a star that is in deep space. The orbit of the planet is considered to be stable and does not change over time. The student claims only experimentally measurable external, The only experimentally measurable external force exerted on the planet is the force due to gravity from the star. Is the student's claim supported by the evidence? What reasoning either supports or contradicts the student's claim? Alrighty. So this goes back to what we were saying. I exert my gravitational influence on everything in the universe, the stars that are billions and billions of miles away. But that force that I pull those stars with is negligible in magnitude. It is absolutely tiny. So it does support the claim because he says the only experimentally measurable. He's not saying that this is the only force. This is the only force that we can measure. And so, yes, that is true. Other external forces are exerted on the planet from other really distant stars and planets and galaxies, but they are of negligible magnitude. Here they're saying the only external force. That is not true. There are forces from other objects in the universe. The strong nuclear force and weak nuclear forces are really weak at these scales. The strong nuclear force stops being an effective force once you get to the size of big atoms. And that's one of the reasons why there's a limit to how big of an atom we can get. Eventually, we put them so far apart that the strong nuclear force between them is very weak, and the repulsion of those protons is very large. Weak nuclear forces only occur in the nucleus. These are nuclear because they mean that they can only act on distances on the size of a nucleus. So they're not going to be able to be measured. We've learned that the electrical force is much stronger than the magnetic force. I mean, the gravitational force. But the electromagnetic forces here are going to essentially be zero because as I accumulate material, charge cancels out. All the positives equal all the negatives in an atom, like the number of protons equals the number of electrons for most stable configurations in chemistry. So there's not going to be a net charge that exerts a measurable electromagnetic force. So A is our best answer choice. 11. An object is placed on a rotating disk. Oh no. The amount of time it takes the object to make one revolution around the center of the circle may be set to a known value. Which of the following procedures could be used to make the necessary measurements to find the coefficient of static friction between the object and the disk's surface?
If I may ask, what force describes magnets? Is it a weak force, a strong force? I don't quite understand what force it lays on.
A magnetism is part of the electromagnetic force. So when we talk about the force between charges, in chemistry, you probably learned about Coulomb's law, Q1, Q2 over R squared times some constant. Now, what we find out is that magnetism is really just electricity when you apply relativistic physics. What that really means is that magnetic forces are really just electrical forces in a weird way. So they're like two sides of a coin. You have a coin called electromagnetism. One side is the electrical description of forces. The other side is the magnetic description of forces. And I don't know if that answered your question, but they're tied in with electricity. And that's why we call it electromagnetic.
Is that why Ersel heard that if you pass a very strong electrical voltage, a potential difference to a piece of metal, it turns into a magnet?
So yes, that's part of it. So like if you wrap a coil around and you apply a current through it, like voltage, electricity, and you put a metal in between it, it'll magnetize the metal and you get what is called an electromagnet. By that virtue, if you pass a magnet around a current, you will change the electricity flow in that current.
So you're telling me if you push enough electric current through a magnet, it loses its magnetic property.
You can induce a magnetic field in the wire that cancels it out. Yes.
Is this what electromagnets are by chance?
Kind of, though an electromagnet is more just like a metal that is not originally magnetized, because not all metals are magnetic, like on a bulk effect. They have little domains that have their own magnetic fields, but a lot of times they cancel each other out. But when you apply a current around it, it aligns all those fields or those domains in the same direction, and we have a bulk magnetic effect.
So is the Earth magnetic because a significant portion of the ore inside of it is magnetic?
So whenever charge moves, it creates an electric field, which creates a magnetic field. And so I'm going to say that we'll save those questions, I think, for physics too. But a moving charge basically creates disturbances in electrical fields, which manifest themselves as changes in magnetic fields. And so yeah, aren't permanent magnets the objects that cause electric domains? So for permanent magnets, it's because their domains align in a way that is the case. And it's because their electrons spin in the same direction, basically. So anyways, let's go ahead and take a look at this one here. Sorry, yeah, we'll save that for physics too, when we deal with magnetism. So if we want to find the coefficient of friction, we had a problem like this in one of our warm-ups. If I have some kind of object on a table as it rotates, we've learned that the force of friction is the centripetal force, which we can say is equal to mv squared over r. So let's see here. Place the disk on the edge, set the disk to rotate at a tangential speed for the object such that the object does not slide. Use a stopwatch to measure the time it takes for the object to make one revolution. That'll give us the velocity. Use a balance to determine the mass of the object. That sounds pretty good, but I don't think we're measuring the distance or the radius of our path. Place the object on the disk and measure the distance from the center of the disk to the center of mass of the object using a meter stick. Slowly increase the rate of the disk until the object begins to slide off the disk, and then record the time in which the object makes one revolution around the center of the disk, and then use the balance to measure the mass of the object. And so I'm going to say that B is our best answer choice here. That's the one that, let's go ahead and see here just in case. But we need to find a way to get M, V, and R. Mu is going to be like, force of friction is mu times the normal force. So that's going to be mu mg for an object on a platform is mv squared over r. Oh, okay. All righty. Thank you. Yeah, I was going to say, let's go ahead and look at the other ones just in case. And so we get mu is v squared over gr. Place the disk, place the object on the disk. Use a motion sensor placed above the disk to measure the tangential speed as it rotates just after the mass begins to slide. While increasing the rate and then use, so this one again doesn't give us the distance. Place the object on the disk and measure the distance from the center of the disk to the center of the mass using the meter stick, okay. Slowly increase the rate the disk rotates until the object begins to slide off the disk, okay, that's good. Record the time in which the object makes one revolution around the center of the disk. Oh yeah, so check it out. If you notice, I showed the work here. We don't really even need the mass. So the mass is irrelevant or extraneous. Sorry, thank you. I did the work here, but I didn't even think about that. Yeah, you don't actually need the mass. If we're looking at just mv squared over r, mass, v, and r are necessary, but that's for the force of friction. We're looking for the coefficient of friction, mu. And mu is going to be given by, or sorry, the force of friction, I put g here, sorry, is going to be mu times the normal force. If I have a block here, the normal force will equal the weight. And then we have the force of friction pulling us in. And so N equals the normal force, or N is the normal force equals mg. Thank you. Thank you there for that. It saved us there, because yeah, I would have gotten like people astray. All right, let's go ahead and continue. It is 7, so that is technically our scheduled time, but we're only about halfway through. So I will be continuing through these. You're welcome to stay. But if you got to go, that is understandable. Let's go ahead and take a look at question number 12. An Atwood machine is placed on a planet in which the acceleration due to gravity on the planet is unknown. Both ends of a light string are attached to two blocks such that M1 is greater than M2. The string passes through a pulley such that frictional forces are considered to be negligible as shown above. The same tension force T is exerted on both blocks and the mass of M1 experiences an acceleration A0 in the downward direction when released from rest. Which quantities will allow the acceleration due to gravity on the planet to be determined? And then let me go ahead and do it in the poll. Alrighty, we'll go ahead and call it here in about 8 seconds. Okay, so if we remember when we were doing Atwood's machines, we were basically asking ourselves, well, what's causing the motion in the system? Well, it's going to be M1G is causing the downward motion, but M2G in this case is going to oppose that motion. So this here is the net force on our system, the weights exerted by the Earth on these two objects. And so then if we want to solve for the acceleration, we can go, or we can just, sorry, that's the net force. And in this case, the mass of the system is just M1 plus M2 times A. And in this case, it's going to be A original. So they want us to try to find the gravitational field strength G in this, like on this planet. So we could say G factored out is M1 minus M2 equals M1 plus M2 times A original. So what do we need? We just need the two masses and the acceleration. Then we can solve for G. Let's go ahead and look at number 13. A scientist designs an experiment that requires two atomic particles whose only fundamental forces between them is the gravitational force. That seems like a very rare event. Which combination of, well, I guess these could be like neutrinos, but no, even neutrinos experience weak force. Between them is the gravitational force. Which combination of particles and separation distance will meet this condition? Very good, very good. I kind of like these other questions that we've had. They kind of set up the discussion so that we can kind of hopefully have some information before we see them. Okay, so we want to find a scenario where the only fundamental force is that due to gravity. So we have to be careful. A proton and an electron are going to experience an electrical force between them. So we probably want to find something that deals with a neutral charge, like neutrons. So maybe a proton and a neutron. A proton and an electron will definitely not be the case. So we're either between A or C as our best answer choices. So here, a proton and an electron within the same atom, even though they're far apart, if you remember the structure of an atom, you know, we have some protons here, some neutrons, protons, neutrons, whatever. Here's the nucleus, and then out here is the electron. The entire reason why the electron orbits around these guys is because there's an electrical force pulling it towards the proton. So sadly, B is not going to be the case. That's the whole reason they're in the atom is because of electrical forces. So we need to find a scenario where the electrical force is not considered. So it's going to be one of these two. Now, what I said was that the nuclear forces act within the nucleus. So we need to be outside the nucleus for this to happen. The size of an atom is about 10 to the negative 10 meters. We call this an angstrom. And you don't need to know that. It's usually kind of written as this symbol here. The size of a nucleus is about 1,000 times smaller than an atom. So that's going to be about 10 to the negative 13 meters. There's 1,000 orders or 3 orders of magnitude difference for 1,000. So we need to be, well, 1 millimeter. Then 1 millimeter is 10 to the negative 3 meters. So this is a lot bigger than these distances. So we're going to want to separate them far enough so that the nuclear forces are negligible, and we're going to want to use like a neutral charge in there so that there's no electrical force. Alrighty, so it looks to me like we have some forces here, some free body diagrams. We have tensions and forces due to gravity. A ball of mass m is swung in a vertical circle, so something like this, with a constant tangential speed. Figure 1 shows the forces exerted on the ball at the top of the circle, and figure 2 shows the forces exerted on the ball at the bottom of the circle. Which of the following is an expression for the centripetal acceleration in terms of the ball, in terms of m, t1, t2, and any fundamental constants? This one's kind of hard, I think. It requires a fair bit of setup. Okay, let's go ahead and take a look here. So if we wanted to do Newton's second law for the first guy, when we're at the top, it's going to be, well, at the top we have T1 and the force due to gravity. Okay. And if you notice, they don't want us to use the force due to gravity in our equation. So plot twist, we're going to have to cancel it out. So this becomes T1 plus the force due to gravity equals m times a. And when we move around in a circle, the acceleration is redubbed the centripetal acceleration, v squared over r. Okay, so that's this guy. When we're at the bottom, we're going to have T2 pointing towards the center. We're going to have the force due to gravity acting down. And so the Newton's second law in this scenario is going to be T2 minus the force due to gravity, because it points away from the center of the circle, equals mv squared over r. So what can we go ahead and do? Well, I think we can go ahead and solve for the force due to gravity, I guess here. And we get the force due to gravity is mv squared over r minus t1. And we're going to go ahead and substitute that into this expression over here. And we get T2, we're going to have to distribute a negative. So I'm going to go ahead and put it in parentheses, mv squared over r minus T1 in parentheses equals mv squared over r. So let's go ahead and combine or distribute this. We distribute this guy, and we distribute it to this guy, and we get T2 plus T1 minus mv squared over r equals mv squared over r. And so we can go ahead and move this over to the other side. They want us to get the centripetal acceleration, v squared over r. T2 plus T1 equals 2mv squared over r, because we're going to add it over. And so it's the same quantity added to itself that gives us 2 of that quantity. And we get v squared over r is T2 plus T1 all over 2m. So D, I think, is our best answer. Okay, yes, this is recording, and then you'll see a link for it on Teams later. Yes, it'll actually be on YouTube. Okay, we're almost in the home stretch. 7 more questions. Questions over this one. I think this is mathematically the hardest one, and it's more algebra and substitution, not actual calculations. All right, so we have a block and a track. A student must determine the inertial mass of a block attached to a horizontal track. The block is free to move horizontally along the track as shown above. Okay, yeah, you also got to go. No worries, no worries. Yeah, I am keeping you guys a little later. Along the track as shown above. Frictional forces are considered to be negligible. The student may only choose 2 measuring tools to determine the inertial mass of the track. Which tools should the student use? And so this one's going to be multiple correct. So we'll go to this one. We'll watch. Yeah, thank you for stopping by. It's dangerous to go out alone. Take these with you. All right. So we are trying to determine the inertial mass of the block. So when we are considering the inertial mass, we should be thinking Newton's second law, m times a. And so we're trying to find this. So we probably want to find a way to get the force and the acceleration. So I think the 2 that will do that for us will be the accelerometer, which will yield a, and the force sensor, which will yield the net force. Because if whatever force is applied to it, that will be the net force because there's no friction to mess things up. If we were thinking stopwatch and meter stick together, they would give us the acceleration, but we can only choose 2. So if we choose this one, we can't choose something else that will give us the force. These 2 in unison only give us the acceleration, but we would still need some way to measure the force because we don't know the mass. That's what we're trying to find.
I may be a little late to the question, but what's the difference between inertial mass and mass?
Okay, so inertial mass and gravitational mass. So there's actually 2 different kinds of masses, but what we find out is that they're basically the same and we just call them mass. Where is it? Oh, I probably put it off to the side. So inertial mass is the mass that we consider when we're talking about forces and accelerations. Like the net force equals m times a. There, really what we should be saying is the net force is equal to the inertial mass times its acceleration. And gravitational mass is the mass that gives us weight or gives an object its weight. Experimentally, what we find out is that they are the same. And because of that, we don't really differentiate between the 2 and we just call things the mass of things. I don't know, did that answer your question there?
So it's just a way to categorize like the different masses, like the different sources of mass?
Yes.
So this question just asking for the inertial mass is just a way to trick you or distract you?
Kind of. Now, be careful here. If the experiment dealt with this object falling, that would be more dealing with the gravitational mass because its weight is what's pulling it down, or the gravitational force acting on that mass.
But the formulas and properties are still the same, though.
Yes. Now, be careful. When I drop a ball here, the only force acting on it is the force due to gravity. And so this is the gravitational mass. And that net force is equal to the inertial mass times its acceleration. Now, experimentally, we have found out that these guys are the same. And this is why we cancel them out. And we say that the acceleration really is just gravitational field strength. Or we call this the acceleration due to gravity. But this is just circumstance in our universe. There may be a universe where they're not exactly the same idea or the same thing or the same value. And so we can't just cancel them out.
Okay.
But yeah, it's just a way to categorize the different sources of mass, or how different sources or different masses affect sources of force. So like this one describes the source of gravity. This one describes the source of like force, if you will. Yeah. So in this case,
I think I understand.
okay. Alrighty, 16. So, oops, this went too far. Let me scooch to the left. A rocket on Earth experiences an upward applied force from its thrusters. As a result of this force, the rocket accelerates upwards at 2 meters per second squared. Assume that there are no other upward forces exerted on the rocket and that wind resistance is negligible. Which of the following combinations of the rocket's mass and force from its thrusters would result in an upward acceleration of 2 meters per second squared? Select two answers. Have a good one. Take it easy. Sorry, I just saw the post there. Sorry. Almost there, guys. Almost there. Sorry. If you need to go, you know, it's understandable. Okay, we're going to go ahead and start working it out. You guys are welcome to continue submitting your answers. So we have a thrust acting upwards, force from the thrusters. And we have some gravitational force, the force due to gravity, which is given by gravitational mass times gravitational field strength, or m times g. So when we do this, we go ahead and we're talking about an acceleration. So we probably want to do Newton's second law, which says the net force equals m times a. And the net force here is going to be the force from the thrusters, which I'm just going to call th thrust, minus the gravitational force. We're accelerating upwards. So I'm going to say that that direction is positive, equals the mass times a. And they tell us that this is 2. And we need to find a combination of these so that the acceleration is actually 2. Well, g near the surface of the Earth is approximately 10 meters per second squared. So we'll use that value. So we get the force from the thrust minus m times 10 equals m times 2. And so we can go ahead and find a relationship for the thrust. The force from the thrust is going to be m times 2 plus m times 10, or really m times 12. So the first scenario here is if I have a mass of 1 kilogram and I apply a thrust of 12 newtons, I will get an acceleration of 2. You could have probably just plugged these in. We get 12 minus 10 equals 2 times a. I'm sorry, 1 times a. Made a mistake there. And we get 2 equals 1 times a. A is 2 meters. That's one of them. So what's the other one that's going to work out here? Well, if you notice, it's a 1 to 12 ratio. So if I triple the mass, then I need triple the force because they're linearly proportional to each other. And we get D. And so here we could go ahead and say, well, 36 newtons minus 30 newtons for the weight is 3 times A. This becomes 6 equals 3 times A. A equals 2 meters per second squared. Or you could have looked at proportions for weight and force. Alrighty. A 2 kilogram object is released from rest near the surface of the Earth. Oh, sorry, from rest near the surface of a planet with negligible atmosphere. A graph of the object's speed as a function of time is shown. What is the weight of the object on the planet? Alrighty. So one of the key things to remember is that if you have a velocity time graph, the slope is the acceleration. And so because this thing is falling with no atmosphere, this acceleration here is the acceleration due to gravity. or what we call gravitational field strength. That's the really annoying thing about physics, is like there's a lot of different names for things. But as Bill Shakespeare once said, a rose by any other name smells just as sweet. So it doesn't matter what we call it, as long as we understand what it represents. So we can get the slope. This is 20 over 5. We find out that G is 4 meters per second squared. Our units are consistent. I almost made a mistake here and jumped the gun. I checked meters per second, seconds. And so we have the acceleration due to gravity. This thing has a mass of 2. M times G is the weight or the force due to gravity. And that's going to be 8 newtons. B is our best answer choice. If we got 10, let me know what we were thinking there. Maybe I made a mistake, but I feel confident about this one.
I just estimated like, oh, 4 seconds, 20 meters a second. I'll just divide. And I got, yeah.
Okay, all right. And then let's see here. You're going to take a, oh, sorry. No, yeah, I already addressed that one. Okay. So an object of mass big M is placed on a disk that can rotate. One end of a string is tied to the object while the other end of the string is held by a pole that is located at the center of the disk. The object is spun on a horizontal surface or on a horizontal circle of radius big R at a constant tangential speed of V original, as shown in the figure. So this bad boy at this instant has a tangential velocity in this direction, such that the tension in the string is capital T. At a time later, the disk is spun such that the tangential speed has increased to twice the value. At a time later, the tangential speed is then increased to a value of 3 times its original value. Which of the following diagrams could represent the forces exerted on the object at one of the given speeds? Assume that the force of static friction is negligible. We will select 2 answer choices here. So this one will definitely, I think, look better on AP Classroom. I think multiple correct. Okay. All right, so let me try to zoom out and do all of these bad boys right here. Okay, so we'll go ahead and end the polling here. And so really what's changing here is the magnitude of the tension. 2, 3, 4, and 9. As far as we look, the normal force and the force due to gravity are not changing in any of these. So let's go ahead and see here. Well, this tension is the only thing acting towards the center of this circular path. So in this scenario, whoops, the tension is the centripetal force. It is the net force pointing towards the center of the circle. So we dub the centripetal force, which is equivalent to mv squared over r. So when I'm going some original velocity VO, well, that's just going to yield a tension T, TO, whatever. When I go to VO, well, then I need to square that, and that's going to give me 4 times the tension. When I triple that speed and I'm going 3VO, that's going to give us a tension that is 9 times as much. So I think the only ones that really describe these are the ones that are in proportion to the velocity squared, which are going to be C and D. Now let me know if we have questions over that one. So this one's just kind of checking, okay, can you recognize proportionalities? These tensions will be proportional to the square of velocity. So we need values that are in proportion to those squares. Let me know number 19. A moon of mass 1 × 10 to the 20 kilograms is in a circular orbit. A planet, or the planet, exerts a gravitational force of 2 × 10 to the 21 newtons on the moon. And they want us to find out the centripetal acceleration of the moon is most nearly. Oh, this one is only multiple choice. Okay, I chose the right one. Sorry. Getting tired of sitting here. My chair is a little uncomfy. Alrighty. So this one can look a little intimidating. It's like, what the heck? What do I do? Well, if we recognize a moon going around a planet, the gravitational force is the centripetal force, just like in that previous question that we had at the beginning. So the centripetal force is going to be the gravitational force. And if they want the centripetal acceleration, they want the gravitational acceleration. Okay, so in this case, well, we can just go ahead and take the force and divide it by the mass, and that will give us our acceleration here, which is going to be 2 × 10 to the 21 all over 1 × 10 to the 20. And so 2 divided by 1 is 2. 10 to the 21 divided by 10 to the 20. This guy's going to have 21 zeros. This guy's going to have 20. That's going to leave us with 1. And so we're going to get an acceleration of 20 meters per second squared. Let me check my math here. Yeah, we just subtract the exponents for the 10. All righty. In which of the following situations is the gravitational force the dominant force? So we're going to go ahead and do a multiple correct here. Oh, shoot. I think I chose the wrong format for the previous one. Sorry. Okay, we'll go ahead and call it in 3 seconds. When is physics C? So it was supposed to be at 7, but yeah, I'm running a little bit late, so we'll start here as soon as I'm done. We're just like 2 questions away, I think. All right, we're going to go ahead and end the polling here for this one. And so our best answer choices are A and B. Here, that would be electrical, and then this one would be nuclear. All right, let's go ahead and look at 21. A student uses a motion sensor to collect data about an object's velocity as a function of time after it is released from rest near the Earth's surface. Okay, you couldn't pick one? Okay, more than one. I thought I chose the right one. I'm sorry. The student claims that the graph shown represents the object while in free fall. Does the object or does the data from the graph support the student's claim? And so we have a velocity and time here. So is it in free fall? Let's see here. Okay, so we'll go ahead and end the polling here. And so we have another velocity time graph. And so the acceleration of this object is the slope. And so we can go ahead and get the slope of this. We're going to go from 0 to 40 in 5 seconds. So delta V over delta T is going to be 40 over 5, or 8 meters per second squared. And so this is near Earth's surface, where the acceleration due to gravity should be approximately 10. So yes, because the object speed increases as it falls, which is consistent, not only does it need to increase as it falls, it increases by a value close to 10. So I'm going to say no, because the slope of the graph indicates that the acceleration is less than g, which indicates that a force other than gravity is exerted on the object, and in this case, in the opposite direction. All righty. 22. So we're going through some points here, A, B, C, D, and they give us the tangential speed at each of these points. Student X ties one end of a string to a 0.5 kilogram ball and swings the ball in a vertical circle of radius 1 meter, as shown in the figure. Student Y uses video analysis to determine the speed of the ball at points A, B, C, and D, as shown in the table. Student X states that the data are incorrect because the tension in the string provides a centripetal force that should cause the ball to travel at a constant tangential speed. Is the student's reasoning correct? Why or why not? Okay. So, alrighty, no problem. Have a good one. So the correct answer here is going to be D. It is not because the net centripetal force exerted on the ball is a combination of the tension from the string and the force due to gravity. So because the centripetal force varies as we move around, here the centripetal force is mg plus T, or really the net force towards the center. Here, T is the net force towards the center. Here, T minus mg is the net force towards the center. And then here it's the same as on the right. So hopefully that kind of makes sense. We'll see you guys on Friday. Have a good one, y'all. Take it easy. Thank you for showing up.
Thank you. A quick suggestion. I'm pretty shouldn't like normal school like integrate this kind of review session, because I feel that what's it called, that being able to see your teacher far after school ends and have these kinds of sessions is very useful. Will you be considering adding these to like your like normal school routine once everything returns to normal?
No, sorry. Spending an hour and a half and then plus some more for another one during the days. Like I need my evenings. I'm doing this because of the AP exam, and we don't really have time in class to review.
Okay, yeah, that's what I thought.
usually do these just as AP exams go on, but no, I mean, I think we all kind of need a break, and this is like an hour and a half where we only have an hour in class or whatever. So sorry.
All right, thank you.
Mr. Gaska, just like super quick question for number 21, the one right before this. Is the slope not like 9.8, or like how did you find that it was like 8 again?
So we went from a value of 0 to 40. So
you use like the exact values.
Yeah,
So you
I
get
mean,
the exact number.
Yeah. So
Okay.
more than anything, I would say this is the line of best fit right here. And so, yeah, it just so happened to go between 2 points that were very nice to work with.
Okay. Thank you. Sorry. Have a nice day.
Thank you.
Thank you so much.
Thank you.
See you. Have a good one. All right. Okay. So give me 1 second. Let me go ahead and sign into Physics C, and then let me know which questions you'd like to look at. That way we can start going over them. And I'm going to assume this is either probably out of E&M, right?
No, this is kinematics.
Okay, alrighty. So I'm in mechanics here. What unit progress check would you like to take a look at?
Can we actually take a look at one of the FRQs
Alrighty.
for the physics day?
And kinematics free response question?
Yeah,
Okay.
any test. I just need a, how can I say, I need to see it done first, so then I have sort of like a template.
Okay, alrighty. So let me go ahead and start copying over some questions here into the OneNote. It's like, that's why we have, like when that kid asked about that, I was like, dude, we have student support sessions. Hopefully,
that's
you know,
fine.
you can make